So this morning we will have the pleasure of hearing a talk from Dr. Ch Chrysostomou, who is, of course, a colleague here at the Cyprus Institute. Let me introduce him briefly to you. He is an associate research scientist with expertise on advanced machine learning and data-driven applications. Dr. Chrysostomou focuses on methodologies for analyzing, storing, manipulating, anonymizing, and distributing big data. Dr. Chrysostomou is currently working and publishing on several applications on machine learning, including characterization and classification of data, genomic and proteomic analysis, fluid dynamics, as well as medical imaging. Dr. Chrysostomou has organized multiple workshops and special sessions related to machine learning and big data analysis. And currently, Haris is the leader of Work Package 7 of the BEATS project that deals with all aspects related to data acquisition systems, 3D tomography image reconstruction, data analysis, data management, archiving and policy, as well as computing infrastructure of the tomographic beamline at SESAME. So there's no better person than Haris, of course, to talk to us today about data analysis and management for the beamline for tomography at SESAME, i.e. BEATS project. So Haris, we are eager to hear your talk. Please do share your slides, and floor is all yours.
Thank you very much, Christine. I will try to share my presentation now. Can you see?
Yes, we can.
Okay. Thank you very much for the introduction. As Kirsty mentioned, I'm an associate research scientist at the Cyprus Institute, and currently I'm the Work Package 7 leader for the BEATS project, which deals with data analysis and management. For this presentation, I will focus on the data analysis and management on itself, but more specifically from the point of the users on what aspects of the computing infrastructure we are currently in designing and building, and how the users can be benefit from this infrastructure. First of all, the overall goal of the Work Package 7 is to deal with all aspects related to data acquisition system, the 3D tomography image reconstruction, the data analysis system, data management, archiving, and policy. These all aspects it's important in regards to have an operational and beamline and the computing infrastructure to keep the tomography beamline up and running. This is particularly important for this beamline because this is one of the most computational and challenging tomography beamlines in regards to data generation and what is needed to collect this data, be able to analyze it, store it, and archive this kind of data. Also, we have some policy-related aspects that we need to deal with as data ownership, and data access and archiving. So before I go into the presentation, I would also like to mention the other participants of this work package, which is the European Synchrotron Radiation Facility, ESRF, the Synchrotron of Light and Experiment Science and Application in the Middle East, SESAME, the Cyprus Institute, and also the Paul Scherrer Institute, PSI. So all these partners are involved in the core operation of this work package, and they all contribute with their expertise. When we talk about data analysis and management, and more particularly for beamline, we first of all we have to prepare and endorse the SESAME data policy. It's the rules that will govern them, not only how the data will generate, but who has access to the data, who is the owner of the data, and so on. Then we have the task for hardware and software definition, depending on the expected users and the expected data, the amount of data generated from this Beamline. We need to define not only the hardware, but also the software needed in order to have a working Beamline, and not to only collect and reconstruct the data, but also serve the users with their needs in terms of analysis. Then when we have designed Beamline in terms of computing infrastructure, then we need to procure the hardware and install it and test it. That means we have to keep in mind the tomography applications that the user will need to use it, and then adapt the data generation and pipelining in order to serve the users in regards to their specific applications. And finally, we have the data analysis as a service, which is a collaboration between Cyprus Institute and SESAME in order to serve the users, not only on the side of the two institutes, SESAME and the Cyprus Institute, but also due to the era of now the COVID pandemic, to be able to do it remotely from their countries. Okay, first of all, I will start with the first aspect, which was the SESAME data policy. And then the data policy more specifically will govern the data ownership, data curation, data archiving, and open access to data. This data policy is already ready and endorsed by the SESAME Council in June 2020. So this document will be available to the users and available to the SESAME website in order for the users to have it as a guideline when they generate their data, who owns the data, how they can access the data, with some associate metadata, and so on. So we define the limits of how much, because there is some storage limit and process limits on the infrastructure, so the user will know for how long the SESAME will be able to store their data, and what it has to be done in order for them to be able to transfer their data in their same institute, and what it means for data archiving, what it will be held by by SESAME for as much as possible, hopefully indefinitely. So this is a very useful document, not only for SESAME to define the rules, but also for the users to know not only their obligation, but also their rights in terms of the data generated. Then I will continue in the hardware and software requirements. In this, we had to follow standard guidelines already followed from the other synchronous facilities, and then specifically find these guidelines in order to accommodate specific scientific cases that SESAME expects from its users. We anticipate a number of experiments per year to be around 20 to 25, so we'll be able to at least accommodate 20 to 25 experiments at this Beamline per year. We had to define the computing powers, not only CPU but GPU, and the special needs that this is in the era of the COVID pandemic. We have to accommodate special needs for online data processing. We have to define the storage sizing depending on the output of the camera, how much data we can collect from the camera, and then also consider the future needs of the Beamline, and to be able to accommodate current and future needs for the specific Beamline for the users. And then by taking because this is not something that we designed the beginning, and then we have entirely from the beginning, you have to take into consideration the available hardware and software available at the SESAME, And also we have some dedicated resources from our side, which is going to, I will explain by the end of this presentation, how not only SESAME can use it, but also how the users can use the infrastructure and the resources from both sides, SESAME and the Cyprus Institute side. When we talk about the software, hardware and software pipeline of the Beamline, we talk about first of all, the acquisition of the raw pixel intensities from the camera. And then we need to have available the software, the infrastructure to the users and SESAME in order to do some raw data processing, which is meant flat field correction, scenogram creation, and so on. And then we go into the reconstruction of the 2D or 3D of the samples. That means Fourier-based iteration or some more advanced iterative algorithms. And then we have the 3D volumetric data, which is going to be available to the users. What we can promise is the pipeline until here, which is the minimum that we need to provide to the users. But we wanted to push a little bit further and to provide some software and some specific pipeline that is going to be used for specific applications, which is going to be like volumetric data processing, which is conversions of data types, noise reduction, ring artifact reduction. And we want to go through some utilities that the user can use in order to do segmentation and quantification of their samples. And this is some of the examples that we can do, like thread halting, region growing, and so on, or geometrical measurements of the size, shape, orientation of the samples, and so on. This we will aim to provide the entire infrastructure available to the users, and we are going to provide dedicated hardware and software for the users in order to do this kind of analysis. This is a more specific diagram regarding the available hardware, which you are going to have the experimental hatch, where is the camera located and the actual experiment will happen. Then we have the bit control hatch, where we will have the data acquisition system for the data to be acquired. And then this will go into the back end of the pipeline, where you will have the GPU and CPU cluster, where the actual heavy it's heavy in resource, needs a lot of resources, where you can have a GPU and CPU and GPU cluster, where you do the pre-processing, reconstruction, and so on. So this is the heavy lifting of the computing infrastructure. And then we have the short-term storage for the users to store their results and the raw data for further analysis. But this is a short-term storage that it will be connected at a certain time and will be transferring the long-term storage. But the users will also have available the data analysis and visualization workstations, which will install a specific pipeline that we would like to do a holistic approach, where we'll have enough software there and enough computing power to cover the majority, if not all, the applications that the users will want to implement. So everything, the majority of the visualization will be done in here at the data analysis and visualization workstation. Furthermore, I would like to go into more specific about the hardware and software required. So, as I said before, we have the short time storage, where the user will keep their own data and the reconstructed data for a certain time This certain time is defined at the data policy, as I mentioned in the beginning. And then after this certain period, the data will automatically be archived in long-term storage. And this will be available hopefully indefinitely. and then the user will be able to request the data even after a certain period. But the user will have the option to take not the option, they are required to take their data with them. So the storage for this short-term storage is, we define it to be half a petabyte would be enough for the first few years. But we also have the long-term storage, which is based on tape-based systems. And these two systems would be enough to accommodate the anticipated number of users for the first few years. But we also always have in mind that this system will be upgraded if more users are, hopefully more users will use this Beamline, and we have the option to always upgrade these storage systems. Next, we have the software. For the reconstruction, we settled on two softwares in order to give more flexibility to the users. The Pi HSTSIM, which is used in currently in ESRF, and Tomography, in order to do the reconstruction and produce them tomography slices and volumes from the experiments, from the samples. Currently, this is an ongoing process. So this software, currently we initialize the pipeline with this kind of softwares, but we are always flexible to upgrade this software if needed, and if the specific application from the users demand. For the visualization workstation, we are going to equip it with tomographic data applications, and here we are going to name a few, like Dragonfly, ParaView, 3D slices, Port 3D, IMOF, and ImageJ. And the aim of this is to use the majority of the software to be free and open access. So we have some applications that are paid and will be available at for the user at SESAME site and the Cyprus Institute site. But the majority of the software is going to be free and open access, so the users will have an easier access and to be able to download them on their own institutes after they leave SESAME or the Cyprus Institute. So they will not be restricted in a closed system where they have to use very specific software hardware in order to do further analysis in their experiments. Another important thing is to have a remote access to the Beamline control and data acquisition system, as well as to the visualization workstation, and this will be granted on demand even after the users leave the SESAME. And then also they will have the option to use, I will explain how later on, how to access also the Cyprus Institute infrastructure in order to do further analysis on their samples and for their applications. This is a more comprehensive list of software that we are going to install on most SESAME side, but hopefully on the Cyprus Institute side, where you have the CT reconstruction, as I mentioned, PyHTS2, but we are going to have NABU and Tomography and so on. So the user will not be restricted in one application, and then they will have more flexibility. And as you see in the open source slide, all of them is open source, and the user will be able to use this kind of software on their own. They don't need to be at the facilities. Furthermore, we also have 3D data processing and visualization, which is like ImageJ, ParaView, Dragonfly, and so on. Also here, the majority, unfortunately, not every software is free. But the majority of these software are open source and free to use by anyone, and then you can download it even now freely from the internet. And here is the links that you can use in order to access this software. Okay, and this we always aim to have in mind the application of the user. in order to do from the computer tomography to simulations of virtual experiments. And this is, thank you, Gianluca, for these wonderful slides of different applications. Finally, is for data analysis as a service. This is important because there is a synergy between the Cyprus Institute and SESAME in order to connect these two institutes and to do and offer this data analysis as a service. Currently, in order to do that, we need to have a strong infrastructure regarding network connectivity. And then what we plan to do is that the Cyprus Institute currently has more than half a gigabyte of direct internet connection, but we have plans to upgrade next year to 1 gigabyte of gigabit per second by the end of 2021. We also have the Cyprus Institute is part of SINET, which is the Cypriot NREN, a national member of GEANT. And SESAME is part of UNET, the Jordanian NREN, and also a member of the Arab States RNE network. So instead, not only the user will be able to have access directly to this to both institutes, but they will be able to SESAME and Cyprus Institute will be able to utilize these two networks in order to transfer their data. And I believe other institutes will be able to utilize these two networks in order to have faster transfer of data between institutes. Okay, currently for storage and computing infrastructure, currently here at the Cyprus Institute, we have the new machine called for high performance computing called Cyclone, which is a supercomputer with peak sustained performance at 600 teraflops. We have 33 nodes available and more than 20 petabytes of long-term storage, which is available. This infrastructure, we are going to use it in order to serve the needs of SESAME for the BIT project, and we plan to do it in two folds. The first one is to have them development and testing in a proprietary on-demand access, which is going to be available for Cyprus Institute and SESAME staff for the code development, and in order to develop the infrastructure of the software infrastructure for the BIT's Beamline. This is already applicable, and SESAME already has proprietary access to Cyclone. And also for the users, which is more important to you, the user will have production access to the machine, where they will have access to the entire machine in order to do the computation, to do their experiments. And this, how much resources is going to Cyprus is going to devote to SESAME is going to be defined by their expected users. So this is going to be reviewed every 6 months, and the resources will be updated. The availability of resources will be updated. But you have to keep in mind that this is a high-performance computing, so we need to follow the rules for a high-performance computing system. And we will be able to provide training to the users on how they can use a high-performance computing system. So usually you don't have access directly, but you enter a queue. But the entire system is available to you when it's the turn of your experiments. This was my presentation. Thank you very much for your attention, and hopefully you have some questions I will be able to answer.
Thank you very much indeed, Hari, for this presentation on the data management and data analysis for the BEAT project. And at this point, I would like to open the opportunity for the participants to ask any questions from Hari. Are there any questions from the floor? Or are there any questions in the chat?
I have a question regarding possibility of mathematics it can be useful, or some interested mathematicians that can do something in data analysis, or only the users, the experimentalists, either physicists or engineers or material scientists, only they do not need that very specific mathematical tools, like in Fourier analysis. Maybe some of the users, they do not have that background. Do you think that mathematics professors in Qatar University also can be helpful or not?
Are you thank you for your question. Are you talking about specifically the SESAME infrastructure or the Cyprus Institute infrastructure, or both?
No, I'm speaking about the users. Users like me, I'm not good in food analysis or all of that. So the software packages will do this for me, or I need
Yes,
some.
the software is going to be, we will have keep in mind that the user will not be expert in this kind of analysis like Fourier, Fourier-based interval reconstruction and so on. The software will be, the pipeline for the reconstruction specifically will be automated. So the user will not be able to, will not be directly involved in that aspect. What you can be involved is the further analysis after you have your trained reconstruction. And I think Gianluca is the Beamline scientist, will be, I believe he can provide a little bit more further information.
Yes, if I can add to that, I think you rose a very important point. Tomography beamlines are naturally, or by definition, a place where mathematicians can have an important role, and a place where research in mathematics and informatics is happening. So there is every day new algorithms for phase retrieval, ring artifact correction, and reconstructions coming out. So you are right. If there is someone interested from departments of mathematics or informatics in Qatar would like to involve and take part in a student project or in a research project, BEATS will be the place where they can test the algorithms and acquire data for as benchmark. So we would be very happy to discuss that. We cannot hear you. Dr. Garaibe, I think you are muted.
Yes, please unmute yourself, Dr. Garaibe.
I'm sorry. My last question is, many thanks for the information. I will share your message for colleagues in mathematics, if they are interested, or informatic department in College of Engineering. The last question that I would like to ask is, as a new users, you will train them about the available software, how to do the analysis while they are in SESAME, and later from Home Institute. You will give some training or something like that, workshops or something for them?
Yes, training will be provided to the user in order to be able to complete their experiments. So I think the training is going to be, I believe, in two folds. One for to use specific software, and the other one is to understand because you have specific software for specific applications. So I think with the Beamline scientist, Gianluca, you need to identify what is the expected outcome, what you want to derive from the experiments. Then you have to identify which software is, and also not only software, but which how you can perform your experiment, because I believe there is different way you can do the experiment with the camera, and then with the help of the Beamline scientists and SESAME, you will be able to guide into the correct direction and then use the correct software and provide training in some extent on how to use it even after you leave SESAME. So training is very important part of this process. I don't know if Gianluca, you want to add something?
Yes, maybe to that, what one should add that we should keep in mind that the pool of users visiting tomography Beamline is very diverse. So you would have one day someone from geology, one day someone from biology, the other day someone for cultural heritage. So providing training and knowing the software needed for all these applications is simply impossible. So there are some steps that are common, opening the data, segmenting the data, some basic image processing steps that are common, and that we will train, of course, and provide support on those. But then it's very important also that the user community, when a certain user has some expertise in one of these applications, it is very important that the user itself gets involved, gets in touch early enough so that we can discuss the application before the beam time, because otherwise it's impossible in 2-3 days of beam time. You sit at the machine and you do the measurement, and at the same time you cannot perform the training in data processing, right? I think it's very important that we start feeling responsibility for this Beamline, and that different users come together as well, because there might be overlaps. So one community might have a certain expertise that can be transported to another community. So for this, we have to start early enough. In fact, even if the Beamline is operative only in 2023, we have benchmark data from other Beamlines. So already next year, for example, we could start discussing pipelines, discussing the available software, testing the available software. So the key message here is get in touch in proper time, much before the beam time, already next year, for example.
Okay, thank you.
Thank you.
Further questions, comments, points for discussion? Yes, Dr. Hannoun, please.
My question is there any bottlenecks for the storage? For the RAM, you have 256 gigabytes in the acquisition system, which is great. I want to know what's like the bandwidth for transferring these images from the RAM to the storage, because this will govern dynamic tomography experiment. For example, with the 256 gigabytes, you can, like if a single stack is 8 gigabytes, you can collect like somewhere around 30 volumes. For example, if you're doing 10-second scans. So I want to know if there is any bottlenecks for transferring the data from the RAM to the hard drives, and this will govern like the dynamic tomography experiment.
Yes, there is a bottleneck, but not from the RAM of the system, it's from the camera. Because there is a maximum amount of frames we can capture from the camera, from experiment. So the bottleneck is there. The system was designed to capture everything that the camera can produce. So and there is a limitation of the RAM, but you have to keep in mind that this is not stored temporarily in order to keep up with the camera. Then we can have a direct transfer of the data into the short-term storage system, which you can start the process also of reconstruction. So this is not a step-by-step process, but this is a pipeline. So you can stream the data. And I believe that currently, and I believe Gianluca can correct me, the bottleneck is on the camera side, not on the computing infrastructure. So I think we can.
Yes, my question is exactly when you transfer from the RAM to the short-term storage, what's the bandwidth?
Is 14 gigabits per second, I think, that connection. So it would be more than enough to it would be more than enough to transfer the data from one system to another.
But Harry is correct. So the standard way in which this camera operates is you are provided by the camera supplier, for example, a backend server with a RAM which is large enough to store your acquisition. So which means that if you go in 4D, at a certain point you will reach the limit of that RAM. We are lucky enough that we can actually collaborate with the Paul Scherrer Institute and the Swiss Light Source, where they have developed data acquisition pipelines for much faster cameras. They have 9 megabyte, 10 megabit detectors that are streaming with much faster speed. So they cannot rely on such a concept, and they have to stream data directly to the storage in the server room. And this is what we will do. So we will bypass the RAM of the backend server. We will have a buffer-based backend writer where we can stream directly on our GPFS, which means that if we do not saturate the speed of the switch, we can in fact stream as much as we want. You're not limited by any RAM size. Of course, if you have some experience in informatics, this is all very much relying on the specific implementation. So since the implementation will be different than the one in PSI, we cannot already we need to build it and benchmark to say, okay, this is our sustained data stream speed, because any software implementation relies on the hardware behind it, right? But the goal is in fact not to be limited by the RAM size of the backend and be able to stream continuously without interruption if you are interested in 4D studies. I think for 4D applications, in fact, what Harry said is right. The limitation will come from the exposure time and by the camera. So for 4D studies, the limitation will be the 100 frames per second that the camera can take. And if you can live with 10 milliseconds exposure time, which also depends on how dense the sample is and so forth.
Yes, thank you very much.